Okay, so in this lesson, we're going to continue our study on cubic functions, so functions that have degree 3. In this particular lesson, though, it says find all zeros of a cubic function. And so the objective is by studying this lesson, given any cubic function, you'll be able to find the zeros. Now, in two previous lessons, we talked about cubic functions. So if you recall, in our first lesson on cubic functions, we talked about finding rational zeros. So in all the problems that we did in this lesson, for example, this particular cubic function, all of our zeros were rational. So we had rational zeros. Then we extended it to this lesson where it said find the real zeros. And remember, a real number can be rational or irrational. So in this lesson, that's where you started looking at, if I can find one real quick, that's where you noticed that a cubic function can also have irrational solutions. So in this particular cubic function, this one right here, if you recall, we had a rational solution, a rational zero, a rational root, and two irrational zeros. We also mentioned, and this is important, we also mentioned that when you have an irrational root, its conjugate is also going to be a zero. So notice that when all the problems that we did, when we had irrational zeros, it came in pairs, plus, minus. All right, and so there was another example real quick where I wanted to show you right here. So notice that in this particular cubic function, we had three solutions. One was rational, two were irrational. And notice the conjugate pair, plus, minus. 1 plus the square root of 5, 1 minus the square root of 5. All right, and so we saw at the end of this lesson that the irrational roots come in pairs, and they're called conjugate pairs. Okay, conjugate pairs. Now, though, what I want to uh, imply or to tell you is that a cubic function doesn't necessarily just have rational or irrational roots. It could have non-real roots. So the zeros in this case could be um, real numbers, or they could be complex non-real numbers. Non-real numbers. So for example, remember a complex non-real number. So a non-real number would be something like 2 plus 3i, something like that. Okay? And it doesn't have to be in the form a plus bi. It could be something like this, negative 2i. So that's what I mean by complex non-real numbers. Also, just like with the irrational roots that come in pairs, complex non-real numbers come in pairs also. All right. So a couple of things before we start looking at examples, a couple of things I want to remind you is this. So recall from previous lessons that complex numbers a plus bi and a minus bi are called conjugates. And the same thing for irrational numbers. A plus the square root of b and a minus the square root of b are called conjugates. And so if a complex number, and what I mean by complex number, I mean the non-real number, like 2i, 3 minus 7i, or an irrational number is a root, then its conjugate is also a root. All right. Now, let's talk about, before we look at some examples, let's talk about the fundamental theorem of algebra. So the fundamental theorem of algebra says this: every function defined by polynomial of degree 1 or more has at least one complex zero. Now remember what we mean by a complex zero. So a complex zero include real zeros. Um, a polynomial function can have only real zeros or non-real zeros, or a combination of the two. It could have both real and non-real zeros. So a complex zero, some students seem to think mistakenly that a complex zero is just a number that has I in it. That's not true. A real number is also considered a complex number. Okay? So in all of our examples, if you go back to the previous two lessons that we did, all of our examples, every polynomial function had at least one complex zero. In our first lesson dealing with rational zeros, they were rational. In our second lesson where we talked about real zeros, they were both rational and irrational, or a combination. All right. So that's what the theorem says. So the fundamental theorem of algebra says this: if you have a polynomial function, then you're going to have at least one complex zero. Now remember, some roots repeat, right? So that's where you have multiplicities. All right, but you'll have at least one. Then we talked about the number of zeros theorem. So the number of zeros theorem says this: a function defined by polynomial degree n has at most n distinct complex zeros. So it has most n distinct. Remember, n distinct means different. So n different complex zeros. And what that means is this: if you go back to one of our, let me see if I can find it real quick. All right, so if you go back to the lesson on rational zeros, what the number of zeros theorem says is this. So notice the degree is 3, right? So the degree is 3. So according to this theorem, the number of zeros theorem, this polynomial has at most three different solutions. Okay? 3 different solutions. Has at most 3. And it did, because notice that each of these solutions were different. So you have 1, 2, 3. 3 different solutions. If you look at this example from the other lesson where we had this function, notice that this function had, remember, it's a cubic, so it has at most 3 different solutions, right? In fact, this one only had 2 distinct real zeros. So remember, we had 2, 3 halves, and 2. It just so happens that 2 occurred twice. So remember, that's where we called it a multiplicity 2, because it occurs twice as a 0. So hence the word multiplicity 2. All right, so we have this has 3 solutions, okay? But this theorem says a function defined by a polynomial has at most n distinct different. So this has 2 different solutions. All right, and it just happens that again 2 occurred twice, 3 halves occurred once. So that's what that theorem says. So as we go through our lesson today, we're gonna mention these things again. So let's summarize the fundamental theorem of algebra. So if you have a polynomial function of degree 1 or greater, and you're trying to find the zeros. So remember, p of x equals 0 means you're trying to find the value of x that makes this function equal 0. So the function p of x equals 0 has exactly n roots, including multiplicities and complex non-real roots. So what that means is, again, if I go back to this one, so the degree is 3, so I have 3 roots, okay? I can have at most 3 different roots. Just so happens that I have 3 roots. I do. Right here, 1, 2, 3. Just so happens, though, that there's only 2 distinct roots because 2 are the same. All right. So that's what the fundamental theorem of algebra says. All right. Okay, so you ready for some examples? And then we're going to come back to this page again. So make sure you constantly look at this page to make sure you understand each little part of this page. Okay, so let's look at some examples. Let's look at example 1. So in each of these examples, you're going to be asked to find all zeros. So find, and they're all going to be cubic. They're going to be cubic. Find all zeros of each cubic function. Okay? All right, number 1. So number 1, let's suppose we had this for number 1. We have f of x is equal to 5x cubed minus 9x squared plus 3x plus 1. All right, now remember, we are still using, if I go back and find that page, we are still using this page, the steps right here. So finding the real or non-real zeros of a polynomial. So this time they're going to be real and or non-real. All right, so we're still using these steps. Okay, so the first thing you're going to do is you're going to find the possible real zeros. I'm sorry, the possible rational zeros, excuse me. So using the rational zero theorem, you're going to find the possible rational zeros. So possible rational zeros. Remember, another word for zero is root. Another word for zero is root. So sometimes you'll hear that word instead. So in my math lab, if you see the word possible rational root, it means the same thing as zeros. Okay, so the numerator, remember, are the factors of your constant coefficient. So your constant term, so 1. So the factors of 1. The denominator are your factors of the leading coefficient. So x cubed is my leading term because it's the largest exponent. And so the leading coefficient is 5. So the factors of 5. So I get in the numerator, the only factors of 1 are plus or minus 1. And the only factors of 5 are plus or minus 1, plus or minus 5. And so you're going to rewrite this better. So you're going to say the possible factors of, the possible rational zeros, excuse me. Possible rational zeros are 1 divided by 1 is 1, 1 divided by 5 is 1/5. So plus or minus 1, plus or minus 1/5. Okay? All right. So let's try 1 first. So we have 1 using synthetic division. There are no missing terms, and it's already in descending order. So I have 5, -9, 3, 1. Remember, trial and error. There's no easy way to determine which one works. Now remember the rational zero theorem. We mentioned this in every lesson so far. The rational zero theorem or the rational zero test or the rational root theorem, whatever you want to call it, only says that if this function has any rational zeros, it's going to be one of those. It doesn't say you will have any. It just says if you do have any rational zeros, it will be listed. It will be one of these that are listed. So we got to find out which one it is if it does. There's no easy way to determine which one it is. You don't have access to a graphing calculator, so you can't use that approach. Okay, bring on the 5. 1 times 5 is 5, so we're using synthetic division. -9 plus 5 is a -4. Multiply. 1 times -4 is -4. Add, we get -1. Multiply, we get -1. And there you go. We found it. So the remainder is 0. So since the remainder is 0, that means 1 is a 0. So what we did next, remember, was we went ahead and we factored this using one of our zeros and the quotient. So remember, this is the quotient now. That's your quotient. The coefficients of the quotient. And so remember what we did. So let me go ahead and write out this first. So we have f of x is equal to 5x cubed minus 9x squared plus 3x plus 1. And so since 1's a 0, that means one of my factors is x minus 1. And this quotient then, this quotient here is these are the coefficients. So since this is cubic, then this has to be quadratic. So that means this will be 5x squared, and this is 5x, and your constant. So this becomes, let me go ahead and move it up a little. So this becomes 5x squared minus 4x minus 1. All right. Now, remember, you want to find the zeros, right? You want to find all the zeros. So what you could do now is you could set this equal to 0 and solve this quadratic equation using the quadratic formula. But I think it's factorable, so let's go ahead and factor this. So we get x minus 1 times, and then over here we have 5x, x, 1, 1. And this has to be negative, this has to be positive, so let's double check. 5x times x is 5x squared. A positive 1 times a negative 1 is a negative 1. The outer is a negative 5x. The inner is a positive 1x. When I add them up, I get negative 4x. And so to find the zeros, I said each one of these equal to 0. So using the zero factor property. And so I get x minus 1 equals 0, 5x plus 1 equals 0, x minus 1 equals 0. You see these right here? X minus 1 occurs twice as a factor, right? So we get x equal 1, that's a 0. We already knew that, right? And over here, x equal negative 1/2. And over here, x equal 1. So notice, remember this theorem. If I can find it real quick. So the number of zeros theorem says a function defined by a polynomial of degree n has at most n distinct complex zeros. Now remember, complex zeros means real zeros or non-real zeros. So non-real zeros is at I. Notice that I have two distinct zeros. So notice, let me write it here. There are two distinct zeros. So there are 1 multiplicity 2, 1 of multiplicity 2, and negative 1/2. All right, and they're all rational. So these are rational zeros, right? Okay, let's look at number 2. All right, number 2, let's suppose we had this for number 2. All right, number 2. Let's suppose this time the function is this. F of x equals 2x cubed plus 14x squared plus 19x minus 2. All right, and we want to find all all zeros, whether they're real or non-real, real or non-real. Sometimes the directions will say, instead of finding all zeros, it'll say something like this: find all complex zeros. And so what we mean by complex zeros is both real and non-real. Okay, so that's what that means, real and non-real. All right. So first we got to do is find the possible rational zeros using the Rational Zero Theorem. So the possible rational zeros. Okay, so we're going to have factors of -2. So that's your constant term. And the leading coefficient is 2, because it's your leading term right here. So the leading coefficient is 2, and the factors of 2. All right. So this right here becomes plus or minus 1, plus or minus 2, divided by plus or minus 1, plus or minus 2. So the factors of -2 are these. Factors of 2 are these. They're the same factors. Okay, then we rewrite this better, right? So we rewrite this in lowest terms. So the possible rational zeros are 1 divided by 1 is 1, 1 divided by 2 is 1/2. So plus or minus 1, plus or minus 1/2. 2 divided by 2 is 1. I'm sorry, 2 divided by 1 is 2. 2 divided by 2 is 1, which we already have. So these are your possible rational zeros in lowest terms. So the Rational Zero Theorem says that if this function has any rational zeros, it will be listed here. All right. Now remember, when we summarize the fundamental theorem of algebra, it says this: if a polynomial has degree n greater equal to 1, which it does, the degree is 3, then the zeros, you'll have at most n zeros, n roots. Roots and zeros mean the same thing. So I have at most 3 zeros, including multiplicities and complex non-real zeros. So when I find the zeros, I'm going to have 3 of them. Now, some of them may repeat, but I'll have 3. Okay? The number of zeros theorem says this: you'll have at most n distinct complex zeros. So I know I'll have 3 zeros, but I'm going to have at most 3 different zeros. That's what that means. Okay? All right. So let's go ahead and try 1 first. Let's try 1. All right, so we're going to try 1. In descending order, there are no missing terms. I have 2, 14, 19, negative 2. Let's see if that works. Bring on a 2, multiply, you get 2. Add, you get 16, multiply, you get 16. So obviously you can tell that that's not going to work, right? So 19 plus 16 will give us 35, and then 1 times 35 is 35, and see, that's not 0. That is 33. So since this is not 0, that means 1 is not a 0. All right, so let's try try 2. So if I try 2, I get 2, 14, 19, negative 2. Let's see what I get there. So 2 times 2 is 4. 14 plus 4 is 18. 2 times 18 is 36. Obviously, you see that's not going to work either. 36 plus 19 gives us 55. And 2 times 55, what's that? 110. And so that's 108, which is not 0. All right. So let's try negative 2. Let's see what happens if I do negative 2. So let's try negative 2. So I have 2, 14, 19, negative 2. So remember, there's no easy way to do this. No easy way to do this. It's just trial and error. All right, so bring on the 2. Negative 2 times 2 is a negative 4. Add, you get 10. Negative 2 times 10 is a negative 20. This may work. 19 and negative 20 is negative 1. Negative 2 times negative 1 is a positive 2, and I get 0. All right, so that's your remainder. So that means negative 2 is a 0. All right, so now what we're going to do next to find all the zeros, we're going to go ahead and factor this using our quotient and the 0. So f of x, remember, what's this? 2x cubed plus 14x squared plus 19x minus 2. So if negative 2 is a 0, that means that my factor will be x plus 2. Okay, x plus 2. Because remember, if I say that equals 0, I get negative 2. So x plus 2. Times the quotient, and this is your quotient right here. That's your quotient. And remember, your quotient is going to be quadratic. This is cubic. This will be 1 less. So quadratic, x squared. So that means this will be 2x squared, and then 10x and negative 1. So I get 2x squared plus 10x minus 1. Now, you can tell from here that this cannot be factored. So since it cannot be factored, this will either be irrational or non-real. So let's go ahead and use the quadratic formula. So what I'm going to do next is I'm going to set each of these equal to 0. So x plus 2 equals 0. 2x squared plus 10x minus 1 equals 0. And so this 0 will be negative 2, which we already knew. So negative 2 is a 0. Now remember, we have at most 3 different solutions. Okay, we're going to have 3 solutions, but we'll have at most 3. So some of these may repeat. Okay, so let's now remember when we said a while ago that irrational zeros occur in pairs, conjugates, and same thing for complex non-real. So when I saw this, since this is quadratic, I'm going to have 2 solutions. They're either going to be imaginary or non-real. I'm sorry, irrational or non-real. So they're going to be different. So I will have 3 different solutions in this case. 3 different. But let's go ahead and use the quadratic formula. So remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So in this case, a is 2, b is 10, c is negative 1. Make sure you write these correctly. All right, I'm going to go to the next page. I'm not going to have enough room down here. So remember, we're solving this. So 2x squared plus 10x minus 1 equals 0. All right, so the opposite of b. So b is 10. b is 10. The opposite of 10 is negative 10. Plus or minus the square root of b squared. So 10 squared minus 4 times a is 2, times c, which is negative 1, all divided by 2 times a, which is 2, right? So 2 times 2. All right, so let's simplify this. So when I simplify this, I get negative 10 plus or minus the square root of 10 squared is 100. Negative 4 times 2 times negative 1 is a positive 8, all divided by 4, right? So I get negative 10 plus or minus the square root of 108 divided by 4. All right, a couple of things I need to tell you. So notice that 108 is not a perfect square, so this is irrational. So this is an irrational root, irrational root. And notice they occur in pairs. Negative 10, so notice negative 10 plus the square root of 108 divided by 4, negative 10 minus the square root of 108 divided by 4. So notice those are conjugates, plus, minus. Now, just to remind you, you can, for me, for a test, you can leave it like this. You don't have to simplify the radical. So you can say the zeros are, so remember one of them was negative 2, so negative 2, and then you can list these separately. So negative 10 plus the square root of 108 divided by 4, negative 10 minus the square root of 108 divided by 4. And notice how many solutions do you have? You have 3. And that's what the fundamental theorem of algebra stated. So given a polynomial function of degree n, in this case my degree was 3. The fundamental theorem of algebra says I will have exactly 3 roots, 3 zeros, including the multiplicities. So notice I have 3, and they're all different, right? I have 1 rational, 2 irrational. So notice this is rational, and these are irrational. Okay. Now I just want to remind you, you see how I listed them separately? No, my math lab. Keep in mind, math lab, they will want them listed separately. But you could have on paper test, you could have just said negative 2 comma negative 10 plus or minus the square root of 108 divided by 4. See, the plus and minus takes care of, you're just writing it both as one thing. Now, on my math lab, they're probably going to ask you to simplify the radical. So simplify the radical. So let's go ahead and simplify the square root of 108. It may not be able to be simplified, but let's see. So let's find a perfect square that goes into 108. So let's try 4 first. So 108 divided by 4 gives us 27. So notice 4 is a perfect square, but it's not the largest because you see that 27? 9 goes into 27, right? So 4 times 9 is 36. So 36 is going to be the largest perfect square that goes into 108. So 108 divided by 36 gives us 3. So 36 times 3 is 108. So that means I can write this as square root of 36 times the square root of 3, which is 6 square root of 3. So what that means is this right here, negative 10 plus or minus the square root of 108 divided by 4. I'm going to write as negative 10 plus or minus 6 square root of 3 divided by 4. And notice negative 10, 6, and 4, they all have 2 in common. So when I reduce this becomes negative 5. Negative 10 divided by 2, 6 divided by 2, 4 divided by 2. So negative 5 plus or minus 3 square root of 3 divided by 2. All right, so another way you can write this is this, negative 2, comma, and then negative 5 plus or minus 3 square root of 3 divided by 2. All right. So on my math lab, they're probably going to want negative 2, and then you have to write these separately. So you can say negative 5 plus 3 square root of 3 divided by 2, comma, negative 5 minus 3 square root of 3 divided by 2. All right. So notice all for a paper test, for your worksheet, this is fine right here. This is fine as well. On my math lab, they usually want your zeros listed separately. So this is what you have to write. And they're also probably going to ask you to simplify the radical. So you are, to simplify the radical, you are going to have to go further with it. All right, so that was number 2. Took 2 pages, didn't it? All right, so let's try another one. Let's try number 3. Number 3. So number 3. All right, let's suppose we had this for number 3. We have f of x equal x cubed plus 4x squared plus 7x plus 28. All right. Okay, so the possible rational zeros, So you have your factors of 28 divided by the factors of 1. So using the rational zero theorem. So the factors of 28 are plus or minus 1, plus or minus 2. 4 goes into 28, so and then 7 as well, right? Because 4 times 7 is 28. 2 times 14 is 28, so plus or minus 14, and then plus or minus 28, and that's it. So those are the only factors of 28. 1 times 28, 2 times 14, 4 times 7. And then the factors of 1 is just plus or minus 1. So your possible rational zeros, okay. And it's all of these divided by 1. So 1 divided by 1, 2 divided by 1, 4 divided by 1, and so on. So your possible rational zeros would be plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 17, plus or minus 14, plus or minus 28. So these are all your possible rational zeros. So the rational zero theorem says that if this function, polynomial function, has any real zeros, it'll be one of these listed. So let's go ahead and try 1, see if 1 works. So 1, and notice there are no missing terms, it's already in descending order. So again, using synthetic division, let's see what we get. 1 times 1 is 1, add we get 5. 1 times 5 is 5, add we get 12. So you see that's not going to work, right? Because 28 and 12 was that 40. Okay, so that's not 0. So let's try 2. So if I try 2, I get, let's see, 1, 4, 7, 28. So bring on the 1. 2 times 1 is 2. 4 plus 2 is 6. 2 times 6 is 12. 12 plus 7 is 19, and that's not going to work either, right? So that's not 0. So let's try 4. So remember, there's no easy way of doing this. Just trial and error. Okay, 4 times 1 is 4. 4 plus 4 is 8. 4 times 8 is 32. That's not going to work. So we know that's not going to work because there's no way you're going to get this to be 0. So that's not going to work. So let's try, rather than keep on, let's try some negatives. Let's try negative 4. Because remember, you can't have zeros out of negative, right? We had that. So let's try negative. Let's try negative 4. 1, 4, 7, 28. 1, bring on a 1. So 1 times 4 is negative 4. Okay, that's 0. That's 0. There we go. Negative 4 times 7 is negative 28. So I do get 0. So that means negative 4 is a 0. Negative 4 is a root. All right. So that means I can factor this now as using this 0 and this quotient. All right. So on the next page, I'm going to use a different page. So according to this, then f of x, remember f of x is this. I'm going to go ahead and rewrite this over. So it's x cubed plus 4x squared plus 7x plus 28. I can factor that. See, if negative 4 is a 0, then remember x plus 4 is a factor times the quotient. And so this is a quotient. So remember this is cubic, right? So that means the quotient is 1 degree less. So this is x cubed. This will be this right here will be x squared. So x squared, x, and your constant. So this becomes, your quotient then becomes x squared plus 7. X squared plus 7. All right, and so now what we're going to do is, obviously you can see this is not factorable. So I'm going to set each factor equal to 0. And I want you to notice that this linear factor right here, that's easy to solve for x. X is negative 4. So you knew that negative 4 was a 0 from here. You already knew that. Over here, this is quadratic. Now you see that x term is missing? See the x term is 0, right? So the x term is missing. I'm going to use a square root property. Rather than using the quadratic formula, I'm going to use a square root property. So I get x squared plus 7 equals 0. And so I'm going to subtract 7 from both sides. I get x squared equal negative 7, right? Then I'm going to take the square root of both sides using the square root property. Don't forget the plus and minus. So one of the things that when students sometimes use the square root property, they forget a plus and minus. Now, they had used the quadratic formula, the plus and minus would have already been in there. So be careful. So the square root and square root into each other, so you get x equal plus and minus. Now remember, square root of a negative 7, remember that's not a real number, so that's that imaginary number. So you get I square root of 7. Because remember, the square root of a negative 1 is equal to I, right? So the square root of a negative 7 is equal to the square root of a negative 1 times the square root of 7, so that's I square root of 7. Remember all that? So notice, remember we talked about the fact that if your polynomial has a non-real number, then its conjugate's going to be a 0 as well. So notice positive I squared root of 7 and negative I squared root of 7. So that plus or minus. So notice the fundamental theorem of algebra says I'm going to have at most 3 distinct solutions. Okay, I'm going to have the fundamental theorem of algebra says I'm going to have three solutions. All right, some of which may repeat. All right, and notice I have 3 distinct solutions. So my solutions are my zeros are negative 4. And if you list them separately, you're going to say I square root of 7 and negative I square root of 7. Remember, always put the I in front of the square root. So that way it doesn't look like, if you put it in back, sometimes y'all make it look like it's underneath and you don't get all your points. So notice 1, 2, 3. So this is rational, which is real. Remember, rational is a real number. And these are non-real. All right? So non-real. Okay. So that was number 3. That was number 3. All right, so let's look at another one. So let's look at number 4. So the more you do, guys, the better it becomes. It's not a difficult idea. Cubics are easy to solve. Okay, let's look at number 4. And number 4, let's suppose we had this. We had f of x is equal to x cubed plus 3x squared plus 6x plus 4. All right, and so the possible, remember this is cubic, so I'm gonna have 3 different solutions. I'm sorry, 3 solutions. I'm gonna have at most 3 different solutions. So I may have some that repeat. So possible rational zeros. All right, so notice in all the problems we've done so far, we had a rational zero that worked. That's not always true, though. That's not always true. But for us, that's the type of problems we're dealing with right now, where you're gonna have one rational zero that works. Okay, so possible rational zeros. So remember, the numerator will be the factors of 4. The denominator will be the factors of 1. So I get plus and minus 1, plus and minus 2, plus and minus 4. And the denominator, the only factors of 1 are plus and minus 1. So if you rewrite this over, possible rational zeros, if you write it over, 1 divided by 1 is 1, 2 divided by 1 is 2, 4 divided by 1 is 4. Plus or minus 1, plus or minus 2, plus or minus 4. Okay, so let's try 1. Notice there are no missing terms, so we have 1, 3, 6, 4. Bring down the 1. 1 times 1 is 1. Add, you get 4. 3 and 1's 4. Multiply, you get 4. That's not going to work because 1 times 10 is 10. So that's not 0. In fact, it's what? 14? So 1's not a 0. So let's try, you know, we always keep doing the positive first. Let's try negative 1. See if that works. Negative 1. 1, 3, 6, 4. No easy way. Just trial and error. Negative 1 times 1 is 1. 3 plus 1 is 4. Negative 1 times 4 is 4. Add, you get, negative 4. Add, you get 2, right? Negative 1 times 2 is negative 2. Make sure I do this correct. Oops, sorry, I messed up right here. Negative 1 times 1 is negative 1. Let's fix this. Let me do this over. Negative 1, 1, 3, 6, 4. Bring on the 1. Negative 1 times 1 is a negative 1. Add 3 and negative 1 is a positive 2. Multiply, negative 1 times 2 is negative 2. Add, you get 4. Multiply, negative 1 times 4 is negative 4, and you get 0. So that means negative 1 is a 0 since the remainder is 0. So that means I can factor this as, I'm going to rewrite this over. So x cubed plus 3x squared plus 6x plus 4. So I'm going to factor this. Since negative 1 is a 0, that means a factor is x plus 1. And then your quadratic, the quadratic here will be the quotient here. So these are the coefficients of your quadratic part. So this is x squared, this is x, and that's your constant. So when I rewrite this over, this is going to be x squared plus 2x plus 4. All right, now it turns out that you cannot factor this. I'm going to have to use the quadratic formula. So what I'm going to do next is I'm going to set each of these equal to 0. Okay. To find the zeros, I'm going to set each one equal to 0. We already know this one. This is negative 1. So we already knew that was a 0. Now let's look at this one. So remember, A is 1, B is 2, C is 4. And remember, the quadratic formula is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So I'm going to go ahead and use another sheet of paper. And so remember, right now we're solving this quadratic equation. So we have x squared plus 2x plus 4 equals 0. So this says the opposite of b. So b is 2. The opposite of 2 is negative 2. Plus or minus the square root of b squared. So 2 squared minus 4 times a times c, all divided by 2 times a, right? So it becomes negative 2 plus or minus the square root of 2 squared is 4. Negative 4 times 1 times a positive 4 is a negative 16, all divided by 2. And so this becomes negative 2 plus or minus the square root of a negative 12 divided by 2. Now don't leave it like this. You are expected to know that you get that imaginary number, right? So the square root of a negative 1 is I. So the point being this, if you want to, you can leave it like this. So you can say, so remember, you see this is non-real, right? So this is your complex non-real 0. Notice they occur in pairs, plus or minus. So if you write your zeros, so the zeros are, the first one was negative 1, and then your other two are these. Negative 2 plus I square root of 12 divided by 2, negative 2 minus I square root of 12 divided by 2. All right, so I did need for you to know that the square root of a negative 1 is I. Notice these are conjugates. Those are conjugates. So remember, one of our theorems says that if you have a complex zero, complex non-real 0 occurring as a 0, then its conjugate will also be there. Okay. So you have 3 different zeros. 3 different zeros. So remember our problem, the degree was 3, so you have 3 zeros. You could have at most 3 different zeros, and you do. You have 3. Okay. All right. Now listen carefully. So on MyMathLab, they're probably going to tell you to simplify the radicals. So let's talk about how to do that. So the square root of 12, you guys simplify this. So the largest perfect square is 4. That will go into 12. So that'll be the square root of 4 times square root of 3. And the square root of 4 is 2, so you get 2 square root of 3. So that means I'm going to go ahead and use this. So we have negative 2 minus I square root of 12 divided by 2. I'm going to replace square root of 12 with this. So negative 2 minus, plus or minus, sorry. Plus or minus I times 2 square root of 3 divided by 2. And I want you to notice something. You see right here, these numbers, they're all divisible by 2, right? They're all divisible by 2. So you've had experience where you had to simplify things like this. So negative 2 divided by 2 is a negative 1. 2 divided by 2 is 1. 2 divided by 2 is 1. So all this becomes this. Negative 1 plus or minus I square root of 3. So all this is this. Okay? So another way you can write this now is this. Negative 1, comma, and then negative 1 plus or minus I square root of 3. On my math lab, they're going to want you to separate these solutions here. So you're going to have to say negative 1 plus I square root of 3, negative 1 minus I square root of 3. All right? Okay. So that was number 4. Let's do one more. Okay, number 5. All right, number 5, let's suppose we had this. Number 5, let's suppose we had f of x is equal to 2x cubed plus x minus 3. All right, so 2x cubed plus x minus 3. So your possible rational zeros are, okay, so remember your factors of negative 3, so that's your constant term, divided by the factors of your leading coefficient, which is 2 in this case. All right, so this becomes plus or minus 1, plus or minus 3, and the factors of 2, plus or minus 1, plus or minus 2. Okay, so you can write this now as possible rational zeros. 1 divided by 1 is 1, 1 divided by 2 is 1 half, 3 divided by 1 is 3, 3 divided by 2 is 3 halves. So plus or minus 1, plus or minus 1 half, plus or minus 3, plus or minus 3 halves. All right, so let's try 1 first. Using synthetic division, let's see if 1's a 0. So notice in all our problems so far, just to remind you, in all those 3 lessons that dealt with the cubic functions, you had one rational zero that worked. You just had to find it. All right, so notice I am missing a term, right? I'm missing x squared, so don't forget you have a 0 here. So 2, x squared, coefficient 0, then 1, then negative 3. All right, bring down the 2. 1 times 2 is 2. Add, you get 2. 1 times 2 is 2. Add, you get 3. 1 times 3 is 3. And notice you get a remainder of 0. So that means 1 is a 0. So once you get that 0, then we're going to go ahead and factor this, and then the rest is easy. So f of x will equal, so if 1's a 0, well, let me go ahead and rewrite this over. So f of x is 2x cubed plus x minus 3. So I'm going to factor this. Knowing 1's a 0, that means x minus 1's a factor. And then here's your quotient. So remember this is cubic, right? So your quotient is going to be quadratic. So 2x squared, x, and your constant. So this becomes 2x squared plus 2x plus 3. I cannot factor this, so I'm going to go ahead and use quadratic formula. So what I'm going to do is I'm going to set each factor equal to 0. So remember, finding the zeros. Set each one equal to 0. All right, so this is linear, so that's easy. That's 1, which you already knew. We knew 1 was a 0. Okay, over here, a is 2, b is 2, c is 3. So remember, negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. All right, so I get the opposite of b, so the opposite of 2 is negative 2, plus or minus the square root of 2 squared, minus 4 times a, which is 2, times c, which is 3, all divided by 2 times 2. So I get negative 2, plus or minus the square root of 2 squared is 4. Negative 4 times 2 is a negative 8. Negative 8 times 3 is a negative 24, all divided by 4. 2 times 2 is 4. Notice you got to get a negative here. 4 minus 24 is a negative 20. So negative 2 plus or minus the square root of negative 20 divided by 4. All right, so I do expect you to rewrite this, though. I do need for you to say that this will be negative 2 plus or minus I square root of 20 divided by 4. So for your worksheet purposes and for your test, it is okay to write the answer using this without simplifying the square root of 20. So the zeros are 1, and then negative 2 plus or minus I square root of 20 divided by 4. I want you to notice, though, remember our fundamental theorem of algebra. Fundamental theorem of algebra says you're going to have 3 zeros. Okay? At most 3 will be different. All right, and you do have 3 zeros, and they're all different. So you could also say zeros are 1. Oops, I think it was negative 1. No, it was 1. So 1, and then negative 2 plus I square root of 20 divided by 4. Negative 2 minus I square root of 20 divided by 4. All right, now if the directions says simplify radical, the direction says simplify the radical, so let's go ahead and simplify the square root of 20 first. So square root of 20, the largest perfect square that goes into 20 is 4, so it'll be square root of 4 times square root of 5. Square root of 4 is 2, so you get 2 square root of 5. So I'm going to go ahead and rewrite this. Negative 2 plus or minus I square root of 20 divided by 4. I'm going to rewrite the square root of 20 using this, 2 square root of 5. So negative 2 plus or minus, and I'm going to, let me do this, I times 2 square root of 5 divided by 4. And I want you to notice, just like we did in another problem, these right here are all divisible by 2. So negative 2 divided by 2 is a negative 1, 2 divided by 2 is 1, 4 divided by 2 is 2. So this becomes negative 1 plus or minus I square root of 5 divided by 2. Okay? So if the direction says simplify, you're going to say the zeros are 1, and then you can say negative 1 plus or minus I square root of 5 over 2. Okay, so the direction says simplify the radicals. This is what you would have to say. On my math lab, you have to rewrite these separately. So you're going to have to say 1 and then negative 1 plus I square root of 5 divided by 2. Negative 1 minus I square root of 5 divided by 2. Okay? All right, so that's going to take care, let me find that first page. So that's going to take care of our lesson on finding all zeros of a cubic function. So you have enough information now. In all these lessons, you have enough information to be able to find all your real zeros, whether they're rational or irrational, and your complex non-real zeros. All right. Now, I want you to also note that all of your zeros are, we say they're complex zeros, because remember, a complex number can be real or imaginary. Okay? All right, so that's the end of this lesson.